Welcome to Module 20, Heat Reg Recovery and Simultaneous Heating Cooling Plants. In this module, we will coordinate heat sources, heat sinks, rejection paths, supplemental capacity, operating modes, temperature hierarchy, failure response, and defensible energy accounting. Heat recovery is valuable only when the sequence proves both sides of the exchange and prevents one loop from creating a hidden penalty in the other. The objectives are practical. You will identify common heat recovery plant arrangements and simultaneous heating and cooling opportunities. You will coordinate heating demand, cooling demand, the usable source, the usable sink, the rejection path, and supplemental capacity. You will define operating modes and transitions, protect equipment limits, account for recovered energy without double counting, and commission recovery, heating only, cooling only, and fallback modes. The core concept is that heat recovery requires more than a cooling demand or a heating demand by itself. A recovery strategy needs a usable source, a usable sink, and a safe path for imbalance. If cooling demand exceeds useful heating demand, excess heat must be rejected or stored. If heating demand exceeds recovered capacity, supplemental heat may be required. The control sequence must prove the source, prove the sink, and know where the imbalance goes. A heat recovery plant is a source-sink coordination problem. The source may be condenser heat, exhaust air, a process stream, or a data center load. The recovery device may be a heat recovery chiller, heat exchanger, or loop. The sink may be heating water, domestic hot water, reheat, ventilation heating, or storage. Supervisory logic verifies temperatures, flow, equipment limits, and economic value. The sequence also needs a rejection or storage path for excess heat. Typical modes include simultaneous heat recovery, cooling with heat rejection, heating with supplemental heat, storage charging or discharging, standby or recirculation, and failure fallback. Each mode needs entry conditions, exit conditions, minimum duration, transition order, valve-proof, pump-proof, and temperature limits. A recovery sequence is incomplete if it only defines normal operation and ignores transitions and fallback behavior. Recovered heat is useful only at a temperature the heating system can accept. Heating water reset and chilled water requirements should be coordinated with equipment lift and efficiency. A system may prioritize the lowest practical heating water temperature and the highest practical chilled water temperature compatible with loads. This can improve recovery efficiency, but terminal capacity, humidity control, and equipment limits must remain satisfied. The recovery machine may be limited by whichever side has lower usable demand. If heating demand exceeds recovered capacity, boilers or electric heat may supplement. If cooling demand exceeds heating use, excess heat must be rejected or stored. Staging should avoid persistent unnecessary boiler firing and tower rejection at the same time. A short transition may be acceptable, but persistent simultaneous waste indicates poor coordination, bad measurements, or missing mode hierarchy. Supplemental heat and heat rejection are not failures by themselves. They are necessary when the two sides of the recovery balance do not match. The problem occurs when independent loops run boilers and rejection equipment without a clear reason. A good sequence recovers useful heat first, supplements only the heating shortage, rejects only the excess heat, and makes the active reason visible to the operator. Recovered energy should not be counted as both cooling savings and heating savings without a clear baseline. Useful reporting distinguishes cooling delivered, heat recovered and used, supplemental heating, heat rejected, electrical input, and avoided fuel or electric heating under a defined baseline. Meter boundaries and calculation assumptions should be documented so the energy story is defensible. The sequence must address loss of a heating sink, cooling source, pump, valve, sensor, storage path, or rejection path. A heat recovery plant can drive temperatures rapidly when a path is lost. Local limits and high priority interlocks should protect the equipment while supervisory logic selects a fallback mode. The alarm should tell the operator what path is lost, which fallback is active, and what field evidence should be checked. Here is the worked example. A heat recovery chiller provides 500 kilowatts of cooling and draws 120 kilowatts of electrical input. Ignoring small losses, condenser side heat is approximately cooling plus electrical input, or 620 kilowatts. If the building can use only 300 kilowatts for heating, the remaining heat requires rejection, storage, or a different mode. Controls should not assume that all available condenser heat is useful recovery. Use this field checklist before enabling or tuning heat recovery logic. Validate heating and cooling demand signals. Document source, sink, rejection, and supplemental paths. Define every operating mode and transition. Coordinate water temperature resets with terminal and equipment requirements. Recognize capacity limits on both sides. Monitor simultaneous boiler and rejection operation. Document energy meter boundaries. Make sure source or sink failure produces a safe local response, and test imbalanced demand conditions. Let us summarize. Heat recovery should be enabled only when both source and sink are proven useful. Define modes for recovery, heat rejection, supplemental heat, standby, storage, and fallback. Coordinate temperature hierarchy with equipment lift, terminal capacity, and humidity requirements. Provide a safe path for imbalance. Finally, make the energy accounting honest by showing cooling delivered, recovered heat used, heat rejected, supplemental heat, and electric input. In the next module, we move to thermal storage, demand limiting, and grid interaction.